In this video, we will cover one of the very interesting topic and is kind of very subjective and very important topic. So, traffic volume forecasting. Traffic volume forecasting we have covered in in a coincidence we have covered in chapter 3 of our video series in detail on how to perform traffic volume forecasting, travel demand modeling, what are the steps, how to do how to do almost everything that is mentioned in the manual in real life. So if you want to learn, so the guideline provide us the name of processes is given in TSAP manual, and another manual we will frequently see is TPP SOP, text dot planning division, standard operating procedure. So these are guidelines where TSAP provides us the name of the guideline to follow, but does not tell us exactly how to actually apply those, whereas TPP SOP tells us how to apply certain aspect. And another one is MPO travel demand models, is where most of the application occurs. So in order for us to learn what are the processes that are used in practice, then we will cover under this chapter 3 of the manual, and exactly with the same name of chapter 3. We have already covered, I believe there are 12 videos on how to actually perform the travel demand model. So we will keep referencing to chapter 3, which we have provided a series of videos. So let's get started. Our traffic volumes are a critical component of any traffic analysis. So if our traffic volumes are wrong, then our entire traffic operations and safety analysis will be wrong. Traffic operations and safety both would get incorrect. So in order for us to design our roadway for a better future, it's very important to have a high quality traffic forecast, and sufficient time and focus should be given to produce high quality traffic forecast, because it kind of determines what kind of capacity is needed for a roadway. For example, let's say we have a 2-lane freeway, and the forecasted demand is 6,000, which is over capacity. Then we might say, okay, we need one more lane. But if the forecasted demand is 10,000, then we maybe need something much bigger than this. So, and then there may be ramps, and the ramp configuration may influence certain things. So if the ramp demand changes from 100 to 500 and it's a weaving section, then this merge can cause several issues. So depending on what volume we are forecasting, our design will heavily get influenced. So traffic forecast is something that heavily influences the design compared to safety and traffic operations. So it's a very essential topic in transportation world. A typical traffic analysis include existing condition analysis, looking at existing data and seeing what the patterns are using existing volumes. Processing existing count into meaningful analysis input facilitates an understanding of several concepts such as peak hour and period selection. We have covered this in chapter 2 in great detail about peak hour versus peak period selection. Local conditions balancing, which we have covered in chapter 3. Outlier data and disruptive events, and validation also we have covered in chapter 3. Processing existing count to uncover several critical traffic characteristics such as design hour factor, directional distribution factor, and T factor. So in chapter 2 we have covered what is K factor, D factor, T factor, how to calculate it, how to use it, which factors to use, which factor not to use. So it's important to not only know this concept, it's also important to know what to use and what not to use. Future year traffic volumes are developed based on historic trend, which is typically past 20 years, but there are new new approaches which looks at past 20 years, then it also looks at past 10 years and past 5 years. Whereas the majority of decisions are made based on past 20 years, is also kind of important to look at 10 and 5 years just to see whether there has been aggressive growth in recent 5 years and whether it justifies using a little bit higher growth rate. But majority of project uses past 20 years as it is. Growth patterns, travel demand modeling. We have covered travel demand modeling and models and Transcad and everything, calibration, validation, post-processing and everything in chapter 3, like I mentioned. Please refer to the video series. It's a really great video series there. Are developed in conjunction with text.tpp division, MPOs and other that perform this type of planning work. So at text.dot there are two different departments. So MPOs are little bit independent of text.dot, but MPOs for major cities for population greater than 50,000. So if a city has population greater than 50,000, then it has an MPO, and then there are MPOs travel demand models. And then on top of this there is text.tpp division, text.tpp division that exclusively work for traffic forecasting. This chapter provides an outline of traffic volume and forecasting process. Like I mentioned, the chapter does not go through how to perform the analysis. It kind of tells us what processes to use. This up to certain extent it does give us some guidelines, but it's not complete. I would say it would be 10% of the knowledge needed in the real life. This chapter also provides procedure to analyze existing traffic volumes and develop future projections. See forecasting checklist for a checklist that can be used during forecasting process is provided in the appendix. For additional guidance on traffic volume and forecasting, refer to text.tpp corridor analysis standard operating procedure. There is a link which is given in appendix which is available to text.employees. So usually we look through the TPP corridor SOP and forecast based on the standard operating procedures by TPP. So that link is given here. However, this link is not accessible to general public. It's accessible by text.employees. Existing traffic volumes. Existing traffic volumes are foundation of traffic forecast. Chapter 2 has information on obtaining existing traffic volumes, which we looked in our previous video. Since we have covered majority of this traffic volume forecast, we'll try to cover this entire manual, this entire chapter in one single video, and we'll see how it goes. It is recommended that existing traffic volumes are analyzed to extract the traffic data factors and process to provide consistent traffic forecast. It is recommended that seasonal variation, historical factor, peak hour, peak period, selection, outlier, disruptive event, balancing and post-processing be considered when using the existing traffic volumes. So when we are post-processing, we can extract a bunch of information which we typically do within Excel through Excel templates. So Excels are set up so they can read the data and kind of spit out this information. Text.dot statewide traffic analysis and reporting system STARS2, which we have talked about in previous video, is a great source of traffic volumes, traffic counts, historical traffic counts. Can provide AADT data. AADT estimates, we looked at what is the AADT in chapter 2. AADT is estimation of daily traffic over 365 days. So sum of all the traffic for 365 days divided by 365 is the AADT, average annual daily traffic. We have looked into AADT, design hour volume, all the concepts that are related to counts in chapter 2 of the video series, fundamentals of traffic operations. A corridor information package can be obtained through request through text.SharePoint. A packet containing information such as 30th highest hourly volume, K factor, directional distribution, and D factor, T factor, average daily traffic, which is different than average annual daily traffic. So there is a difference between AADT, average annual daily traffic, and ADT, which we have explained in greater depth in the video series. A design hour volume and vehicle classification. A graphics of 30th highest hourly volume is given here, which is used traditionally to calculate K factor, which is mentioned here. However, this is an outdated approach. I believe TxDOT has in past used this approach, and majority of state DOT still uses this approach, and it is recommended within the TSAP manual, but there are better guidelines on how to calculate T factor. So let's look at what is the 30th highest hour data. 30th highest hour data is, we took the hourly data for the entire year and entire year for every day, and then we figure out what is the 30th highest hour by volume, and then we compare the highest hour volume divided by a daily volume for that day. So this is a very old, not very old because we still use it. This is how K factors are calculated, but we have discussed what are the disadvantages of using K factor based on locations and how this K factor can be misleading. So several DOTs, specifically Florida DOT, has started to move away from this outdated approach of using 30th highest hour data because it's tricky, because this data is based on actual data, and actual data can be misleading, which we have covered in chapter 2 again, how the data can be very misleading and how the K factor can be misleading. So FDOT has moved away from using 30th hour data to use a standard K factors by facility type. Standard K factors by facility type, which can be modified for different locations, which I believe is a better measure of how the demand varies, because K factor, like we have mentioned in great detail, that is a property of a region, of what time people in certain region go to work, what time they come back, what time they go to movies and stuff. It's not a property of roadway. So D factor is, so K factor should ideally be calculated by certain region and how the certain region population is behaving, and it would eliminate a lot of limitations that are there because of the restriction on traffic count. So traffic count can give us some information which many times can be misleading, especially in urban areas, and the approach of using standard K factor eliminates that issue. So I believe currently Stars 2 gives us K factor for majority of roadways in Texas, and when we request the TPP corridor package, we receive the K factor within the TPP corridor package. However, going forward in future, I would really like to see this K factor approach being changed the way Florida DOT does, of standardizing the K factor. That eliminates a lot of limitations we currently have. But for now, the way manual is K factor. There are two sources of getting K factor, like I mentioned, for TxDOT, which is Stars 2. We can get it from data, and we can get it from TPP corridor package, and we have discussed in great detail on which one to use and what priority should we take, especially if we are collecting the data on what kind of data is better than other kind of data for calculating the K factor. So please refer to chapter 2 of the video series we have, Fundamentals of Traffic Operations, which discuss in great detail about what the K factors are, how it's calculated, how it has been traditionally calculated, what are the new developments, and and which sources are better to be used. Now next one is traffic data factors. The common traffic data factors include K factor, D factor and T factor. The K factor is 30th highest hourly volume and is presented as percentage of ADTs. Again, this is a very traditional approach. K factor is basically peak hour volume versus daily volume. That's all K factor is. But traditionally we have calculated is as the 30th highest hour volume and divided by daily volume. This is a traditional approach which is now being revised in several states. The D factor is directionality of 30th highest hourly volume. It is also expressed as percentage of ADT. The T factor is total percentage of single unit trucks and multi-unit combination of trucks. TxDOT uses vehicle classification data and overall traffic volumes to determine the T factors. So we have talked about K, D and T factor in greater length on AASTO classification and which one is called what. We're not going to repeat the same information, so you can watch the other video series where this information is provided. TxDOT uses data to develop equivalent single axle load ESAL. ESAL is another important concept that is used in structural and pavement design, which we have covered. Calculation for pavement design. Traffic data factors are obtained from TPP corridor information package for most of the projects. The TPP corridor information packet may include traffic analysis for highway design document if available on the STARS2 data. Next one is seasonal factor. ADT is calculated using a volume count, axle factor and a seasonal factor. So we have looked into how ADT is calculated. If we have 365 days of data, then we can directly calculate ADT. However, if we do not have 365 days of data, which we mostly don't, then we have ADT multiplied by seasonal factor multiplied by axle correction factor. So then we can use the daily counts to change into ADT, and we have discussed about all the small things about these factors again in chapter 2. Historical factors we have covered in chapter 3. Historical factors are developed by calculating traffic growth rates between the past year and at multiple locations within and near the study area. It is suggested that historical growth rates are developed for as many years as the available data, which is typically 20 years. It is suggested that regression analysis be performed on historical count to determine average linear growth rate. So in Texas, we have discussed the difference between annual compounded growth rate and linear growth rate, and in Texas we use linear growth rate. The growth rate factor is determined based on average growth rates. Check the traffic data to access whether it is necessary to exclude any outlier from the analysis and document accordingly. So several times in the STARS2 there are abnormal data, and we need to check for those abnormal data and take them out of the calculation. An example of historical growth rate calculation is provided in this appendix. This appendix is pretty much is TPP. It comes with TPP corridor package. It uses linear regression to come up with growth rate for 20 years, 10 years and 5 years. It also gives the confidence level at 90% confidence, the upper and lower limit on the growth rates. Also, it gives a way to calculate the growth beyond 20 years. So let's say our existing count is 2023. Let's say our base year for the analysis is 2025, or this is also called opening year. And let's say our design year is 2045. Then the growth rate we typically calculate is applied for next 20 years, which will go up to 2043. But between 2043 and 2045, after 2043, the growth rate, let's say, is 3%, is usually pivot to default of 2%. So in Texas, a default of 2% linear growth rate is applied after 20 years, which is called pivot growth rate now, in majority of cases. So between 2020, if we want to forecast for 2045, which is design year in future, we can use the historical growth rate up to 2043. Beyond 2043, we have to apply the pivot growth rate. Peak hour versus peak period selection, we have covered this, so we'll skip this one. It's mostly looking at the traffic count and figuring out the peak hours, plotting the counts like this, northbound versus southbound. I believe these are mainland data. It looks like from the counts it looked like one lane data from in two directions. So we have discussed at great length about peak hour and peak count, and how peak hour are used and how peak counts are used. Disruptive events, this is something new and interesting that has been added to TSAP manual, and it's a very good guideline, because many times what happened that during COVID the ADT went down. So typically ADT increases, but as soon as COVID happened, the volume on the roadway went down, and then it slowly went up again. So let's say this is 2020, year 2020, it went down, and then by 2022 it climbed back up again, as a generic trend. So disruptive event can be and are very, very tricky to handle in when we are calculating historic growth rate. So if we are in 2023, now the question is whether we should be, when we are calculating the growth rate, whether we should include this data or not include this data, or if we have collected the data here, whether we should use it or not use it. So those kind of guidance is given here. So existing traffic volumes can be affected by disruptive event. During disruptive events such as pandemic, data collection may need to adjust to account for anticipated impact of disruption and to remove outlier. So options for obtaining data during disruptive event based on disruption type, duration, data availability, and data limitations. If the data is less than 2 years old, so that's the guidance number one. If the date, let's say the COVID happened in 2020, then if the data is less than 2 years old from the start of disruptive event, so if this data is up to 2018, then we can use the data as it is. Use data as it is. In other situations, lack of recent count can create need for counts to be grown with historical growth rate or validated by big data sources. Big data uses geolocation service. We have looked into it to sample the number of users. Again, the sample size affects the quality of data and quality of results they can provide. Figure 3.3 shows a decision tree to help decide what method to use for traffic analysis. Description of 4 types of analysis are presented on following page. So the first type is recent count. When the recent count is available, this is a very good figure, and it's a very good guidance on how to use recent count. So if the recent count is less than 2 years before the onset of disruptive event, then we can use it as it is, as long as we are not far away from disruptive events. Then forecasted count data. If we can collect the data, we go and collect the data. But if we are, let's say we are living in 2021 inside the COVID situation, then this guidance applies more. But if we are in 2025 where things are back to normal, we can simply collect the new counts and move along. So I believe this guidance is more important during the disruption. So let's say a COVID pandemic started in 2020 and ended in for example, let's say 2022. So during this time period, if we are working on projects, then we would look for data before 2020. So we will look between 2018 to 2020 or end of 2019 data, and if we find this data, we will use it as it is. That's the guidance number 1, as it is. However, if the data is available between 2016 to 2019 is 2 to 5 years old, 2018, if it's 2 to 5 years old, then we will use historic growth rate. The third one is use big data with nearby counts. Use big data validated with counts near the study location. The big data can be validated using volumes that existed prior to disruptive event and are typically the average of several months. So when we are using big data, we can look at the big data sources. The good thing about big data is it can give us existing and past, so we can look at what was the count in past, then validate that count in past with stars2, and if the validation goes through and it looks like the big data in past looks good, then we can use a chunk of big data within that region for our analysis. And big data without nearby counts, use the big data by taking the average of 3 to 6 months. It is recommended that data be used an average of typical period with 3 to 6 months period. So if we have nearby stars2 count, then we validate the big data and use it. If we don't have nearby stars2 count, which is rare because stars2 counts are almost everywhere, and then we can take the average of 3 to 6 months using the big data sources. Big data are tricky. It's better to validate them because it depends on the sample size, and in future they are gonna play a bigger role, which we believe, but presently their accuracy may be limited, but we do believe that in future their accuracy will go up and they will become a major source or a major disruptor in transportation industry as in general. Next we have traffic balancing. So when we collect the data, usually along the main lanes, traffic are balanced within plus minus 10. So we need to balance them such that the difference between on ramp, off ramp are 0. So let's say that we have 100 vehicles here, 50 entering, then we need to have 150 vehicles here, and let's say out of these 25 vehicles exit, then we have 125 vehicles left. So we need to balance them out such that there are 0 vehicle difference on the main lanes as well as on the frontage road or arterials. On the arterials, if there are major driveways, then we put them as intersections. If they are not, let's say there are smaller driveways with 5 vehicles, 10 vehicles, then we assume them that they are gonna come from the nearest intersection, or we just balance them such that we are not losing any volume in between the intersections. So that's the traffic balancing. We have covered this in traffic volume forecasting. So traffic volumes are considered balanced when no volume discrepancy exists between adjacent locations. Balancing typically begins from one side. So you start from here, then look at this ramp, then figure out whether this is balanced, then look at this one, then figure out this is balanced, and move up to the end. So let's say we are missing 5 vehicles here, then we will add something here, then add something here, then here, and it continues. Similar with the frontage road, we change something at one intersection, which changes how many vehicles are exiting, which changes how many vehicles are going through, which changes this one, then changes this one. So typically some imbalance, we try to manage the imbalance of plus and minus. Plus is source and minus is sink. If there are source and sink, then we can balance it easily, but if there is only imbalance which are source, then it continues to propagate along the frontage road. So that's the traffic balancing. Traffic balance base year volumes and traffic forecasts. It is recommended that the counts are balanced before the analysis begin, though there may be circumstances where counts will not be balanced. Usually counts are not balanced on arterial and frontage roads. So almost in 99% of cases they will not be balanced. Actually, no, they are balanced on the main lanes plus minus 5, but not on the arterials. In not balanced due to land use and specific traffic generators, before balancing begins, round the count to nearest determined interval unit. So round them to nearest rounding. There is a rounding which we have provided in chapter 3. However, the guidance here is a little bit different, so we will since we work on TechStart we will follow the guidance here. So traffic volumes are typically rounded to nearest nearest 100, but if the traffic volume is between 100 to 200, so first one we have 0 to 100, the second one we have 100 to 200, and I think we have 200 greater than 200. So between if it's greater than 200, then it says traffic volume typically are rounded to nearest 100, which is mainly AADT, so rounded to nearest 100, but are rounded to nearest 50 if traffic volume is between 100 to 200. Between 100 to 200, nearest 50. This seems very excessive. The rounding procedures we had were different. This seems a little bit unrealistic, but it's 10 to 25. So we'll try to send an email to TSAP committee to see whether this is what really they want. Please refer to one of our guidance we have provided based on NCHRP report and FDOT guidelines, and I believe there is a FSWA studies that goes through this guidance. This one seems a little bit excessive in terms of rounding. Next one is validation. Validate existing volume by checking against the field observation historic counts. So once we get the counts, we need to validate it whether the counts collected has been done properly. Figure 3.1 and 3.2 shows the capacity of basic freeway. So we also need to check them against the capacity. Typically for freeways, the count cannot exceed the capacity. So if the capacity is, let's say, 2100, and if we see a count of 3000, then we can see there has to be some problem with the counts. So we need to compare the counts with capacity. Typically we don't need to compare. We usually have a number in mind and we can visually see whether there are some unrealistic counts. So capacity changes with free flow speed, but the typical freeway capacity we need to have in mind is 2300, this number. So somewhere between 2300 2400 is what we need to have in mind as the capacity number. The next page we have the ramp capacity. Typical ramp capacity I usually consider is 2100. So we don't need to be very precise, but I need to have a number in mind while we are playing with a traffic count. So we don't go and actively apply table 3 and 3.1 and 3.2, but it's kind of a is inside engineer's head, that when we look at the calculations we can visually spot if there are outliers by using this ramp capacity around 2100 and the freeway capacity around 23 to 2400. These are good number to know. Similarly, for an intersection, for the critical lane volume, we kind of know that usually it's around 1600 to 1800. And these are good numbers to have in mind, so we don't go and calculate everything by hand. And these are something we can do in our head and spot the errors quickly. Forecasting traffic volume. So this section describes a different methodology to forecast traffic. Forecasting traffic volume involves existing volume at growing existing volume at a given growth rate, which is growth factor method, which is the method 1 we have discussed. This section discusses forecasting traffic volume with latest travel demand model outputs, with latest demand model outputs, and a hybrid of demand model output and no travel demand model output. So this chapter discusses what to do when we have the travel demand model, when we don't have the travel demand model, and many other things. So for projects within the boundary of an MPO, there are 23 MPOs in state of Texas. So for projects within the boundaries of MPO, the latest MPO travel demand model outputs can be referenced to determine the corridor growth rate. So when the MPO travel demand models are available, they take a preference over other data sources. The good thing about travel demand model compared to historic count is it captures the future. So travel demand model captures the future, whereas growth rate captures the past. So travel demand model in a sense is a better tool as long as the model output are of good quality. So sometimes the model outputs are a little bit tricky to handle, so we have covered how to spot the output, whether the output is good, output is not good, how to process the data, and how to process the good output versus bad output. We have covered everything on calibration, validation, and post-processing in chapter 3 of the video series. For projects outside of MPO boundaries, we can use TPP statewide analysis model. SAM is developed by TTI, Texas Transportation Institute. So if we are within the 23 MPOs I mentioned, we will use MPO's travel demand model, and if we are outside, then we can use a statewide travel demand model. Statewide travel demand model captures in the entire state. So most likely the corridor we are working on, at least the TxDOT corridor we are working on, are included in SAM. For the forecasting, without travel demand model, growth patterns and historic trends are used as a mean of estimating future volumes. The traffic analysis for highway designs for adjacent project in an additional so if sometimes there are traffic analysis for the highways from the nearby project which has already the projections, which can be additional resource for the projections. For typical traffic forecasting process, it is recommended that traffic growth rate from the various data sources be documented and submitted as a part of traffic projection methodology memo. So before doing the actual forecast, we write traffic projection methodology memo, which includes the corridor package, TPP corridor package, which gives us historic growth rate. It also looks at a little bit of TDM output and TDM based growth rate, and then it also looks at census data. Then it also looks at traffic impact analysis in the area, and if there are some other available nearby projects. Although TPP corridor growth rate is extensive, many times we have our own growth rate for the corridor. So what we do is we collect 20 years of count at more locations than the corridor package and present them. So we also along with the TPP corridor package growth rate, we calculate growth rate based on stars 2 using 20 years of data using linear regression. So growth rate for first 20 years is typically higher than growth rate for more than 20 years because the growth will taper over the years. For additional guidance on traffic volume and forecasting, refer to TPP SOP. Okay, so the way to calculate the growth rate is we calculate the growth rate based on historic counts, which we can get from stars 2 and TPP corridor package. Then travel demand models, if the MPO travel demand model is available, we use 23 MPOs. If there are if the our roadway lies outside of MPO, then we use SAM model. US census, we can look at the population growth in the area. It's a little bit tricky to use population growth. For example, if we are working on a city and the interstate goes through it, let's say this is an interstate, then majority of traffic, let's say this is a small town, then majority of traffic traveling on the interstate may be through traffic which is just passing through the state. So the growth in the traffic will depend on how the traffic is going to develop from one big city to another big city. So even though we look at US census population data, and then engineering judgment needs to be used. Engineering judgment on what proportion of this corridor traffic is coming from the population and what percentage is coming as from outside of the city we are considering. Then planned developments, this is another important source of traffic which changes the traffic growth rate. Many times when we work on projects, we calculate growth rate from TDM, we calculate growth rate from historic counts, and let's say we come up with 3%. However, many times there are a lot of undeveloped roadways and a lot of communities are getting built, and if once we focus on certain zones, then we see that this intersection is going to grow at much higher pace because there are 3,000 extra vehicles coming from here, 2,000 extra vehicles coming from here, 10,000 extra vehicles daily coming from here. So then we anticipate this intersection or this location to grow at a higher pace. So planned development, which is like traffic impact analysis, plays a major role in changing the growth rate or volumes. Adjacent projects, if we have data from adjacent project, then we can use those and combine them together to come up with one single growth rate or come up with a logic to calculate future traffic volumes. Traffic volume forecast approval process, we have discussed it several times, and there are 3 approval process: option A, option B, option C, which is described on the next page. Option A is used when everything is summarized here, however described in detail on next page, which will switch to next page. There are 3 options of approval. Option A, within an option A, the major steps are a district request TPP to analyze traffic data. So here district is text.district. So text.district sends an request to TPP to create the data. TPP generates the requested projections in accordance with TPP division SOP. Then TPP provides the final approved traffic data. So TPP itself generates and approves. So TPP generates plus approves. By approving, it means they sign the forecast to be used and send it back to district, which in turn send it back to consultants. So this is option A. Most widely used option is option B. Option A is typically not recommended when preferred alternative is not set. So let's say we are working on a corridor, and in majority of corridor the preferred alternative is not set. So if the preferred alternative is not set and we want to change this ramp configuration from looking like this to an exit and entrance, then if the forecast has been approved by TPP and developed by TPP, and if we are changing the alternative, then we have to go back to TPP again for some major changes. For minor changes it may be okay, but for major changes we have to go back to TPP and start this process, and this process takes a long time. Typically we can say between 2 months to 4 to 6 months. So this process is used when the preferred alternatives are set. So when we already have a good knowledge on what we are looking for example PSNE projects, if we are doing any traffic analysis for PSNE projects, then we can use because at PSNE schematic is done and everything is kind of set, so we can use option 1. Option B is what that is frequently used in industry. In option B, district requests the TPP to prepare consultant corridor package. This gives us historic growth rate. It also has a lot of other information, but historic growth rate is the one we mostly use. Then the consultants prepare the traffic projections memo, and TPP reviews and approves the traffic projections memo. So consultants, before actually forecasting, they create the methodology memo. Which goes to TPP for approval. Once TPP approves it, then we consultants actually do actual forecast, which goes back again to TPP for approval. So that's the option B. Option B, consultants do the work and TPP approves it. The good thing about this process is it gives flexibility to change multiple alternatives. So if there are 4 or 5 alternatives, then a consultant can develop all those alternatives and send it to TPP for approval. And if there's something changes again, then we can revise the forecast and send it back again for TPP for approval along with what has changed. In option C, the role of TPP is simply replaced by district, especially in metro cities. So TPP role is replaced by TxDOT districts. So especially in metro cities where districts has a good technical capability of approving forecast, then district may speed up the process by approving the forecast by themselves. So in this one, district requests TPP approval to district requests TPP approval to perform and approve the traffic analysis. So instead of TPP approving the forecast, district requests that district is going to perform and approve the traffic analysis. Using this option is more typical for metro district that has proper resources to develop, review and sign traffic analysis. TPP prepares the corridor information package. So corridor information package is still provided by TxDOT TPP division. Consultants prepares the traffic forecasting memo for district approval. So here, instead of sending it to TPP, it is sent to TxDOT division. So methodology memo is sent to TxDOT district, which after approval from TxDOT district goes to consultant, and then the actual work happens, and then it goes to TxDOT district for approval. TPP provides the eCell data. Several times this forecast, which gives us AADT, is fed back to TPP, which calculates the eCell data based on the future volumes. Coordinate with TxDOT project manager regarding the latest guidelines, since the TPP may be changing the procedure to eCell calculations. So even in this option, we need to send the forecast back to TPP so that TPP can calculate the eCell data. One important thing to remember about eCell data is the AADT needs to be balanced to 0 digits. So one of the typical comment we receive from the TPP on the eCell data is the unbalanced volumes and a mismatch in growth rate. So growth rate for 30 years should be less than growth rate for 20 years, and volume must be balanced. These are two typical comments we receive from TPP division when they are producing the eCell output. Volume must be balanced. Next one, we have future year selection. So the next one we have is future year selection. Typical traffic forecast includes project opening year, design year, and pavement year. So we have discussed let year plus construction year is typically the opening year. 20 years from opening year is the design year, and 10 years after that is the pavement year. An interim year, the traffic forecast may also include an interim year. I think it's around 30 to 50% of projects does include interim year. An interim year is the opening year of different phases of project for after the first phase. So interim year may be necessary if the project's improvement, so failure level of service prior to design year. So several times, no matter how much improvement we are doing, we try to build a system so that it works with acceptable level of service till design year. However, no matter how much capacity we are providing with the limited funding we have, we may not be able to provide acceptable level of service. So what we try to do is we try to look in the future how long the system would work and up to what point our design would work, and then beyond what time there may be more improvements needed. So that's one use of interim year, is when the system is not designed to last till design year, then we try to see whether it can last up to interim year. The second use is if there are different phases of construction. So let's say we are working on a project with one direct connector that will be built and open to public before the second one is built. So then we can do the interim year analysis where one system is built and open while the second one is gonna build in another phase. That also triggers an opening year analysis. Next one, AM PM peak hour traffic volume projections. Here is a little bit the actual projections are a little bit tricky than what is mentioned here, but we'll first look at what is written in the guidelines. AM and PM peak hour are not always inversely related. So let's say AM traffic in this direction is 200, AM traffic coming in another direction is 10. So it doesn't mean like people are going in this direction 200 in PM peak, they would come back at 200, and in this direction it would be 10. Usually PM peaks are much higher than AM, so in PM peak this may be 600 and this may still be 50. So directionality switches between AM and PM, but exact number may not necessarily switch. The peak hour percentages in terms of percentage of daily traffic that is occurring in AM and PM can be determined separately for both peaks, and the percentages are intended to be a representation of existing traffic patterns. So this discussion in this paragraph are when we have existing ADTs, also from some sources or by forecasting. Let's say we have future ADT but not future AM and PM. So we have future ADT, and in existing ADT we can calculate out of daily traffic how much is occurring in AM, how much is occurring in PM. Then we can apply the same factor to get how much AM traffic will be there in future and how much PM traffic will be there. Next, we have typically turning moment counts are collected in form of turning moment counts and segment counts. Assuming that traffic counts are taken over a typical weekday with no major events or disruption, they represent peak hour percentage of AM, peak hour percentages for AM, PM K factors. The peak hour percentages are then applied to ADTs to develop AM and PM peak hour volumes. It is recommended that traffic count collected be validated against the STARS2 data. So instead of using one K factor, we can call it AM factor or AMK factor, and PM K factor. It's not really a K factor, but let's call it AM factor and PM factor. Turning moment traffic projections are estimated by applying existing turning moment counts percentages at each approach to ADT volume. This is wrong. This is a traditional way. So let's say in existing 50 vehicles are turning left, 100 vehicles are going through, and 50 vehicles are turning right, and the total traffic is 200. In future, if we have 400 vehicle here, the what guidance says is our traffic volume turning moment traffic projections are estimated by applying existing turning moment count percentages. By that definition, this would become 100, this would become 200, and this would become 100 again. Turning moment counts are typically rounded to nearest 50 vehicles in increment. These are for ADTs. It avoids an overestimation on each side street. Traffic projection can be balanced along the corridor. So the issue with this approach is, let's say in future there is going to be more traffic turning left because there are shopping malls here and there are new developments here. If we use the fixed percentage approach, these numbers will always be a constant number, whereas we know from the travel demand model or land use and that this left turn is going to go up. Maybe this through is not gonna grow up. Maybe in future this left turn needs to be 150, this one needs to be let's say total is 400. So let's say from 100 in existing it grew to 150 again. So these two are 300 and this right turn is 100. So this is 400, but it's different than this number because from land use pattern we can see whether this left turn movement is going to increase or not, and this is where table demand modeling and a lot of engineering calculations comes in play. This guidance is for a higher level when the land use and all those are not considered. So we cannot just simply take the existing percentages and just apply on the future to calculate the future traffic volumes. That's a little bit of naive approach, I would say. The better approach is to figure out the traffic pattern, estimated traffic pattern in the future, and then apply but however we will still maintain the existing ratios. So we have looked in a greater detail on how to calculate future turning moment volumes given two things, given existing turning moment counts and future estimated link volumes. So what we want to do is we want to still maintain the future turning moment count percentages. However, we also want to consider what is going to happen in future. And this kind of deviates a little bit from text.sop. It's a better approach. Text.sop does not consider the land use pattern and other changes to estimate the turning moment count. So it's a little bit deviation, but a better approach is to combine these two together, which we have discussed in great detail, which can give us a better estimate of turning moment count. So the approach here is called fixed percentage approach, whereas a better approach is typically needed in traffic volume forecasting world, where we are not only dictated by what is happening in existing, we also take care of how the future is going to look like, mostly future land use patterns. Model version control, if we are working on no build and build scenario, then we can rename them with different model numbers, so that if we need to roll it back for some reason, or in many times we need to look for the previous model, then we can look at it easily. Forecasting with travel demand model outputs. So this section kind of talks about the forecasting with travel demand model outputs. So TxDOT has and 23 MPOs collaborate in transportation planning process and in development of travel demand model outputs and their inputs. The 23 MPOs are listed on the next page. The MPOs can be referenced to determine the corridor growth rate for a project. The MPO TDM output can be referenced to determine the corridor growth rate for a project if available. Outside of this MPOs, then TxDOT TPP SAM, which is developed by TTI, I believe, can be referenced to determine the growth rate of a project. SAM involves travel demand modeling at a statewide level. It includes different passenger and freight models and interaction among these models. Access to MPO travel demand model and the SAM need a data request, which we typically get it from our TxDOT-PM. There are 4 different type of travel demand model, which includes general trip-based model and activity-based models. There are different type of travel demand model which we have looked in greater detail. The first one is a traditional 4-step travel demand model, and then activity-based model. So traditional 4 demand include trip generation, trip distribution, mode choice, and traffic assignment. Activity-based model include trip going from one zone to another. So from morning they may go to work, then go to come back home, then go to shopping, then come back home. So this is activity-based model. Activity-based models are more used in metro cities. For Austin area, the MPO model is Campo, and for Austin area, the travel demand model we use is 4-step. We have discussed all these things in greater length, so we'll skip it here on what are different kind of models that are there. Now let's look at the next important chapter, important discussion, which is here. Travel demand modeling includes the selection of applicable model, calibration, which we have discussed in 2 of our videos, local conditions, validation and model result, and a revision of forecast, which is also post-processing. A travel demand model is calibrated for regional trip distribution, mode choice, and assignment. These are on the development of travel demand model. However, when we receive a already built travel demand model, we still have to calibrate them. The travel demand model output can have inconsistency, which they typically do on a link by link basis, since these models are not calibrated at link level, like we have mentioned and in a very detailed hour-long videos. Therefore, further adjustment and post-processing of models daily and peak period outputs are typically applied prior to use in corridor and projects. And there is a guideline, NCHRP report 716, that goes through travel demand modeling parameter estimation techniques. It is recommended that the TDM output and growth rate be validated with other sources such as historic data, adjacent project, past project, state demographic factor, and US Census population. When forecasting a volume with a travel demand model, the existing year of the travel demand model coincides with date. These are some detail about travel demand model which we can ignore. These are the development of travel demand model itself, which we typically don't need. We will skip the trip generation, trip distribution, mode choice. This has been discussed in much greater length. Next one is if we are working on a forecasting that does not have travel demand model, then what we can do is we don't have travel demand model output either from MPO or from SAM. Usually SAM covers everything, but let's say the quality of output from SAM for that particular region is not that great. Then we can obtain the existing volume, determine the historic growth rate, apply the growth rate to existing volume, and look at the other consideration. This is called growth rate method, which is method 1 of what we have discussed. Method 1 of chapter 3 of video series. Obtaining existing volumes. So existing volume considerations are discussed in previous chapter, how to obtain them. For just as a refresher, for turning moment count, the guidance is to collect 2 days of data. For segment counts, the guidance is to collect 7 days of data, and for FSWA project 14 days of data, and for classification count 7 days of data. To determine the determination of growth rate, so what we do is we combine all the data sources. We look at historic growth rate, we look at population growth rate, we look at travel demand model output, and then we combine them together to come up with a common growth rates. So apply the growth rate to existing volumes. Other considerations are listed here, which is plan development, adjacent project. Plan developments are mostly covered under travel demand model, but if there are developments that are not considered, then either we can code it inside the travel demand model, which is tricky, or we can consider it externally after post-processing. Sometimes there are adjacent projects which has already done the forecasting, so we can reuse their numbers and kind of save time, budget, and effort. Forecast using hybrid approach. This is something that has been added, it's very interesting. So the hybrid approach to forecasting volumes involves historical growth rate data and a travel demand model output. There are 2 types of hybrid approaches. While both approaches uses historical growth rate and travel demand model output, the order in which they use is different. So first one is use the historical data and historical data plus travel demand model output. So first we get the historical growth rate from here. The hybrid approach involves historic traffic data and patterns. So we have historic data, then growth rates are calculated from TDM output. So TDM output will give us growth rates, and growth rate will be applied on historical data to calculate the future volumes. This is approach 1. Approach 2 is a TDM output. The TDM output numbers and the growth rate, and this first one is the typical process what we typically use for projects. The second one is taking the TDM output and applying historic growth rate on it. So hybrid approach involves obtaining a travel TDM traffic data. Growth rates are calculated from historic data and then applied to TDM volumes to forecast traffic volumes. So several times if the TDM growth rate is not available, for example if we are doing a route study, then in travel demand model that particular route may not be drawn. So let's say we draw those draw a new route which is bypassing the existing route in travel demand model. Now we can, to generate the future numbers, we can take the existing OD and apply a growth factor to generate future OD, and then run the travel demand model to see how it reacts. Several times, another good example would be several times we have existing TDM OD and we have existing big data source OD, existing OD from let's say Bluetooth sensor or big data sources, and if we think that the TDM OD is far away from existing OD, we take the existing OD or a combination of both, and then we calculate a growth rate externally and then we grow it to calculate future ODs. This is applicable in the case where a new route, when there is a new route location, historic data is not available, or considerable development and land use changes are expected in project area in the future. The next we have connected and autonomous vehicles. The important aspect of connected and autonomous vehicles is the increase in capacity. So depending on increase in roadway capacity. The connected and autonomous vehicles are move a little bit closer to each other. Their driver behavior may be different, but we are not talking about the driver behavior here. We are mostly interested at this level is increase in roadway capacity, because vehicles are kind of driving closer to each other. So in the connected and autonomous vehicle, when they are 100% connected, then the capacity goes up to 3200, which is 33% increase. And based on varying level of proportion of connected autonomous vehicles in traffic, these are adjustment in capacity. So we can take this adjustment and code it in the travel demand model links, or this is already built in highway capacity software, where we can define the percentage of the CAVs and we can analyze the results. So in forecasting world, we can change link capacity, which will result in pulling more traffic on the roadway. We have discussed this again in greater length in the video. And in traffic operations world, we can simply improve use it within the highway capacity software, which takes this percentage as input. That's the discussion on connected and autonomous vehicles and how to handle connected and autonomous vehicle within travel demand model and traffic operations. And that covers chapter 3, which is traffic volume forecasting. So it's a great chapter to have. Please refer to our video series on actually how to perform these calculations and some of the guidelines that are mentioned here, and some of the improvements which we have covered in chapter 3 videos. Thank you very much. And next one we will look at another important topic, which is tools selections. So tools selections is a very important topic, because depending on what tools and methodology we are using, we will end up with different time and budget. So depending on what approach we are using, this chapter 4 applies to the beginning of project, and maybe towards end throughout the project, but mostly in the beginning. It's very important to figure out what tools and approaches we are going to use, so we can figure out how much time and budget we need to scope for. So we'll discuss about chapter 4 starting next video. Thank you.